Great. So we're very happy to have Netta's last lecture today.
Right, thanks, Veronica. Everyone, welcome back. So last time we talked about quantum extremal surfaces, and we talked about some of the strange behavior of quantum extremal surfaces, such as the fact that the quantum extremal surface of a region R does not have to coincide with the quantum extremal surface of its complement. And that turns out to be extremely important for some recent developments in quantum information in AdS CFT. So today's plan is extremely ambitious, and we may or may not get through all of it. So I'll try to slightly modify where the document camera is standing, so my hand does not block the paper. Okay. Okay, so today, first, we're going to start with an argument for why, not really an argument, I'll just outline how this works. The reconstructability of the entanglement wedge. So we're going to talk about the Dong-Harlow wall argument for why we can reconstruct not just up to the causal wedge, but really all the way up to the entanglement wedge. And I will emphasize when we do this that argument relies on a number of aspects of the dictionary that really only work to within first order quantum corrections, where you're not including back reaction and you're not computing the quantum extremal surface, but just the classical extremal surface. And once you start including quantum extremal surfaces and back reaction, then things become very different. And we find that there's a particular state that has a privileged role in the reconstruction, which is a maximally mixed state in the bulk. The role of the maximally mixed state. And finally, there have been quite a few questions this whole week about complexity of reconstruction and how hard it is to reconstruct behind the causal wedge. So I'll wrap up with complexity of reconstruction and the so-called Python's lunch proposal. Okay, are there any questions about this or last time? Okay, so part one. Reconstructability of the entanglement wedge. Okay, so how do we know that we can reconstruct the entanglement wedge? You've heard this a lot, you've seen it in other lectures already, but we haven't really justified why is it that we can reconstruct the entanglement wedge from the perspective that we've been taking this all along of, you have the Ryu-Takenagi surface, the Kubini-Rangamani-Takenagi surface, and so on, like the Faulkner-Lukowitz Moldasina proposal. We haven't justified why we have to be able to reconstruct the entanglement wedge. Now, we did say that it seems likely that you can, because you would expect that you can compute minus trace rho log rho, and that means you can compute the area of a surface that lies behind the causal wedge. But for argument's sake, you could imagine that you can reconstruct the entirety of the causal wedge and then maybe bits and pieces of what's behind it, and maybe not everything behind it. So how do we know that we can reconstruct the entirety of the entanglement wedge? And to understand this, we need one final ingredient, which is the relative entropy in AdS CFT, and in particular the so-called JLMS proposal. So let me remind you what the definition of the relative entropy. So if we have two states, two density matrices, rho and sigma, then we can write the relative entropy in this way. Rho log sigma, which we can also write as minus S rho plus trace of rho K sigma, where K here is the modular Hamiltonian, that's minus log sigma. Okay, so this is the modular Hamiltonian. So the relative entropy is a really nice quantity because it can serve as a distinguishability measure between two density matrices. So if they're identical, it's going to be 0. So we can think of this as sort of a distance between states. There's another type of distance, a trace distance. It does not coincide with it, but it is a good measure of distinguishability between the two states. Now, in order to work with this argument, with the Dong-Harlow-Wall argument, we're going to be, at least for the moment, working purely to first order into quantum corrections, meaning we're not including any kind of back reaction. And for purposes of this, we'll also be considering just Faulkner-Lukowitz-Maldacena, meaning the classical extremal surface is the one that we're using. So we're going to work to first order in quantum corrections. Okay, so let's consider now two states. So consider two states for density matrices on the region R. So notation do I want to use? Okay, so rho R and sigma R. Now, as you've all already seen in Michael's course, when we do bulk reconstruction, we have to be working within some code subspace. So I'm going to heavily rely on Michael's course and Patrick's course for this lecture. So I hope you were there. So we need to consider some code subspace in the bulk. And so we're going to be working with these two are in the same code subspace. And in this case, the code subspace we're considering is one where we have some classical geometry, we have some quantum fields propagating on it. Okay, because again, this is what we're working with. These two states are basically very close to one another, and they're propagating. We can think of them as two states that are propagating on the same classical background. So this code subspace is basically quantum fluctuations around some background. And we have some classical extremal surface, XR, which computes the von Neumann entropy to leading order, and then we'll have some follow-up contribution. That's the von Neumann entropy of these quantum fields. So what JLMS, this is how we usually refer to this, it's Jafferis, Lukowitz, Maldacena, and Su. Should abbreviate JLMS. What they argued is that the relative entropy of the of reduced density matrices on the boundary equals the relative entropy of the corresponding states in the bulk. So S rho R sigma R, so this is a boundary quantity, is equal to S rho HR, so this is the homology hypersurface. I'll draw a picture in just a second. Sigma HR plus order G Newton corrections. So pictorially, we have some region R. This is our classical extremal surface XR. This is HR. Okay, so this is just some homology hypersurface. It doesn't have to be static. We can be looking at some time-dependent case. It's just a homology hypersurface. And these two density matrices are defined on this homology hypersurface. And what Dong, Harlow, and Wall argued is that essentially the JLMS relation, this equivalence between the relative entropies, implies that the entanglement wedge is reconstructible in the dual CFT. And I'll say a little bit about how that's done, but I won't go into too many of the technicalities. So Dong, Harlow, Wall. So they argued WER is reconstructible from dual CFT using JLMS. So what's the intuition behind this? So the intuition is that the relative entropy is a distinguishability measure. So suppose, page.
Could I ask a question about this equation before you move on?
Of course.
I'm just forgetting how these terms all work out.
Mhm.
Should I really expect that correction to be order G Newton, or should I expect it to be non-perturbative?
You should expect it to be order G Newton. Remember just once you're looking at these types of corrections, the extremal surface itself will move. So you don't expect this. I mean, if you can actually hold on to that question for maybe 5 minutes, then I will address exactly why I'm assuming we're working to leading order, what happens when you work to subleading order, all of this breaks down.
Mm-hmm. Cool.
Other questions? Okay, so let me pull this up a little. Okay. Okay, so suppose, let me draw a Lorentzian picture here. So this is D of R. This is C of R, the causal surface. And we have some our XR over here. And we say, suppose that, so this, the entanglement wedge looks something like this. And we say, okay, suppose that we know we can reconstruct the causal wedge, that's just HKLL. And when I say reconstruct here, I mean reconstruct the bulk quantum fields propagating on it. And so suppose we can't actually reconstruct the entirety of the entanglement wedge. Then if this is our HR, then there could be some subsets of HR that we just can't reconstruct. Somewhere over here, we just can't reconstruct those subsets from the dual CFT. But if you then say, okay, suppose now that I have two states, suppose that I have rho HR and sigma HR, which are identical in the causal wedge. But they differ in the entanglement wedge. And maybe they differ exactly in those subsets of this complement region here that we can't reconstruct. Then if there is a region of HR that we can't reconstruct, then we would not know that rho HR and sigma HR are not the same state if they only differ on those subsets that we cannot reconstruct. So if those two states are the same everywhere, except on those subsets we can't reconstruct, then we would say they're the same. But then we would have a problem with this formula here, because this formula here tells us that the boundary states are as distinguishable as the bulk states. And so in a very rough intuitive sense, again, I'm not going through the derivation, I'll be a little bit more precise in a moment. This tells us that if this formula is true, GLMS is true, then we have to be able to reconstruct everything on HR. Because otherwise it could be two states could look indistinguishable, two bulk states could look indistinguishable in the CFT and actually not be the same. So that is the sort of 30,000 foot intuition behind the proof of Don Carlo wall. Other questions about the intuition?
I have a small question, which is if you have this argument seems to be based on the fact that the distinguishability must be larger than subleading, right?
Yeah.
Like
So yeah.
Different, which is order G Newton, then I guess that doesn't contradict.
Yeah. So I'm going to defer all higher order corrections to by now probably 3 minutes from now. And then I'll discuss all of them. Everything I'm saying now is really like you should only take it to be true at first order quantum corrections. After that, there are very serious problems, and I'll talk about those. In fact, I can't really resist saying this, but so that what you saw in for example in Michael's course is that the bulk is the way that the bulk is encoded in the boundary is a quantum error correcting code, and in particular you saw that the type of code that you were looking at was an exact quantum error correcting code. And it turns out that once you include corrections, you actually have to talk about approximate quantum error correction. So, but that comes later. I won't say much about the details of approximate quantum error correction, but I'll talk about the salient points of why things kind of have to be very different. Okay, so just maybe I can be just maybe ever so slightly more precise. So essentially the way that that John-Harlow-Wall do this is they say, okay, if rho HR equals sigma HR, so a little more precisely, or maybe the same thing I just said, but in equations instead of words. So JLMS implies that if rho HR equals sigma HR, then S of rho R, sigma R equals 0, is order G Newton. And from this, you can show, which implies, I'm not going to show you how to do this, but you can look up the original John-Harlow paper, John-Harlow-Wall paper, it's DHW. You can show that there exists a quantum channel. Let's call it N, from density matrices on the Hilbert space of the boundary subregion, the boundary Hilbert space, to density matrices on the space, on the bulk space, such that this channel acting on rho R is even going to be equal to rho HR. So this essentially is the statement of bulk reconstruction. There exists this channel, and you can actually execute the reconstruction. So this is this, yeah.
Isn't it important that the same channel also does it for sigma? Because this is just trivially true. I could have a constant channel that sends everything to rho HR.
I should have said there exists a single channel that will work for, yeah. That's right. N is not rho dependent. And in particular, so you could say, okay, so you can reconstruct this. This shows you that indeed can reconstruct. And in fact, Faulkner and Lukowitz actually gave a constructive protocol for this. It's sort of inspired by HKLL, but everywhere where you would normally use the boundary Hamiltonian, you end up using the modular Hamiltonian. So it's more complicated, it's more non-local, but it works in a very analogous way. So now there have been enough questions at this point about subleading corrections that I should probably begin to address that. But let me ask if there are questions first on just the first order quantum corrections, just quantum fields propagating on a Kirk background.
Hi, yes, I have a question. In that quantum channel and in that argument, what's the role of sigma? Because the end statement seems to just depend on the rho, so that's why I'm confused.
Well, so as John mentioned, the same channel has to also work for sigma. That's very important.
Oh, okay.
Yeah.
Okay. Thank you.
Other questions?
Does the same protocol, like the constructive protocol, does that only work for pure AdS, or does it also work for like general asymptotic AdS space times?
It works as long as you don't expect your quantum fields to strongly back react on your, as long as basically you can put the quantum state that you want on some fixed geometry and do the reconstruction there. So we don't expect that you need to be working in pure AdS in it, although you do need to know the metric in order to write down the sort of you still have to write down the smearing function that depends on the metric. So it only works for reconstructing the quantum fields in the bulk, not the metric itself. But there's no reason, as long as you can find this mirroring function for a given geometry, and as long as your states are consistent with not having strong back reaction on it, then you can use it for non-pure AdS spacetimes.
Okay, thank you.
Other questions?
I had a quick question.
Yeah.
So, I mean, it seems like in order to construct the bulk, you first need to ensure that rho HR is equal to sigma HR. Now that is also related to the bulk. So, I mean, before you reconstruct the bulk, how can you actually make sure that that holds?
So you have to assume that a bulk exists. And so, but this statement is just saying that it's just a relation between the bulk and boundary states. So you say if GLMS is true, then this implication is correct. That's all. You don't need to know what rho HR or sigma HR are in order to do this constructive protocol. For the proof, though, you say there exists a bulk, there exists a rho HR, there exists a sigma HR, and then if they happen to be the same, then you can then this follows, and from this you can prove what you want.
Okay, but I mean, I was thinking if you have a particular boundary and if you want to construct the bulk corresponding to that boundary, then you need to, in order to apply this procedure, you need to first ensure that rho HR is equal to sigma HR, right?
So this is not a procedure, right?
Okay.
This is just a statement. It is possible to do this.
Okay, I got it.
Yeah.
Thanks.
This is an actual constructive protocol. Other questions? Okay, so as you've all noticed, I've been very cagey about the additional quantum corrections. So let's ask what happens when we start adding additional quantum corrections. So higher order corrections. So let's consider again the statement S rho R sigma R equals S rho HR sigma HR. And now we're working to all orders in perturbation theory. So if we're including all quantum corrections, then we know that the quantum extremal surface in this state does not have to be the same as the quantum extremal surface in this state. So I'm going to see if I can draw a picture without it being too busy. So we have some R, it doesn't have to be half the boundary, it's just easier to draw this way. And let me use different colors, might be easier to see. So suppose that we have this here, the blue, is the quantum extremal surface when the bulk quantum fields are in the state rho bulk. So we're going to call this chi R comma rho. Hopefully you can actually read this. Okay, now suppose that the quantum extremal surface in the sigma state is different. So maybe this is the quantum extremal surface in the sigma state. So this is going to be chi R sigma. Now we have two different homology hypersurfaces. We have this one, this purple one, and I will call this one H R sigma. And we have this homology hypersurface. And I'll call this one H R rho. So then we have to ask ourselves, okay, what actually goes into this relative entropy formula? Do we evaluate the state of this rho, for example, or sigma? Let's say, okay, do we evaluate sigma on, do we take sigma H R rho? In other words, the trace of the complement of that over the bulk state sigma? Well, we could do that, but this doesn't have any meaning from the perspective of the boundary entropy, because for the boundary von Neumann entropy to compute that kind of thing, to compute the modular Hamiltonian, we have to be evaluating the bulk state on its own homology hypersurface. So this state, we can define it, but it doesn't actually make sense. It's something that we can feed into a formula or that we would then relate to the state sigma r in the boundary. So no. Well, then surely we should just say, okay, we're just going to evaluate, this is going to be, just down a little bit. We should clearly evaluate S of rho, H r rho, and sigma on H r sigma, right? Except this, it lives in a different subspace from that. These are two different Hilbert spaces that we're defining here. So we're not going to be, we don't want to compute the relative entropy between these two states that live on two different subspaces. So also no. Okay, so how are we supposed to make sense of this relative entropy formula? Well, we're not really supposed to make sense of it, but then we can ask, well, what about reconstruction? How much of the bowl can we actually reconstruct now? Let's take a look. So draw a picture. I guess maybe, let me bring the same picture back. Okay, so we have this one. Now, suppose that I have some operator, some bulk quantum field over here. Let's call it phi of y, since we're using x for the quantum extremal surface. Okay, so we have this phi of y here. Well, phi of y lives both in the entanglement wedge of this state and in the entanglement wedge of this state. So, okay, we say, great, we can reconstruct it sort of no matter which state we're in. What if it lives over here? Phi of y prime. If it lives over there, then it would appear that we actually can only reconstruct it if we have this state, and we cannot reconstruct it if we have that state. So I want to emphasize that, we're talking about two states here in the same code subspace. So it's not like saying, oh, you have two different geometries, and we have this state lives here, and then the state, this phi of y is prime here, phi of y there, and it makes sense that it's different. This is the same small code subspace that we're talking about, and we can reconstruct an operator sometimes, and sometimes we can't, and it sort of seems to be very heavily state dependent. I also want to emphasize this is different from the quantum error correction story that you saw earlier in St. Michael's class, where you said, okay, there was a question of whether your operator that you want to reconstruct lives in R1 union R2, or it lives in, it doesn't live in R1, so it doesn't live in certain entanglement wedge of certain boundary subregions. This is not the same thing here. This is the same code subspace. It's the same boundary subregion. It's the same bulk, theory. And the only thing that's different is we're looking at the two different states in the same code subspace. And we're finding that sometimes we can reconstruct this state and sometimes we can't. And so the really important takeaway here is that quantum extremal surfaces are state dependent, which means that we're going to have to deal with a certain amount of state dependence in our reconstruction, even if we're talking about a small code subspace. You might be tempted to say, probably this only happens when you have a large amount of quantum effects. Maybe you have some black hole in the bulk, but this is actually not the case. So I want to say, well, okay, I want to actually give credit to two groups of people who have figured this out. So initially, this problem was discovered. So initially discovered by Hayden and Pennington. And in the framework of approximate quantum error correction, and also discussed in by Levine, Akers, Leichenauer, and Levine. So the example from Akers, Leichenauer, and Levine is very instructive because it's kind of an easy example, an easy case to see where you can have a very small code subspace of low energy excitations and still run into this problem, as long as you're considering quantum extremal surfaces and not classical extremal surfaces. So suppose that we're looking at two intervals. So we have two candidates for the classical extremal surface, is pure AdS. And also, if we're looking at the vacuum state, two candidates for the quantum extremal surface, it's the same thing, it's extremal. And you could say, okay, suppose we're just right at a transition point between them, where the areas of this have the same as the areas of that. Then let's drop in a few EPR pairs. If they're entangled across this surface, then if we cut across this entanglement, we're going to gain, remember what we're computing is the area of X over 4G plus S bulk across X, HR. So if we then say, okay, if this were the dominant quantum extremal surface, then what would happen is we would be cutting across this entanglement. So we would incur more of this over here than we would if we used this one. So suppose that before we had maybe this one was ever so slightly dominant, just had a slightly smaller area. By introducing enough of these EPR pairs, we could run into the problem where the bulk entropy is enough to overcome the area contribution, or even more easily, we could have the following situation where the areas are identical. And we say, all right, let's suppose we add some entanglement here. That makes this the relevant quantum extremal surface. But also that makes this the relevant quantum extremal surface. But if instead we added some entanglement across this, that would make that the relevant quantum extremal surface. And those are two states, two bulk states we can take to be in the same small code subspace. And they would have two dramatically different quantum extremal surfaces, dramatically different entanglement wedges, and dramatically different reconstruction. There will be very different regions of the bulk that we can reconstruct with one versus the other. Now, of course, what you can do at this point is you can shrink your code subspace to the point where it has no such states that have significantly different quantum extremal surfaces. So one possible attempt at ignoring this, burying your head in the sand. Well, you could say, let's shrink the code subspace. Shrink the code subspace. But, well, there's a limit to how much you can shrink it. You can't shrink it to be trivial. Why can't you shrink the code subspace to be trivial? You say, I just want my one state that I know where the quantum extremal surface is, and then in some trivial sense, my bulk reconstruction is not state dependent. The problem is, if you only have one state, then you can't turn on operators, and then you're not going to be reconstructing your operators. And so in what sense are we really talking about bulk reconstruction? So you can't take a trivial code subspace, and as soon as your code subspace is not trivial, then maybe it's small enough so you don't have to run into this issue, but it's not obvious that for every bulk geometry and for every choice of boundary interval, you can always choose a code subspace that's going to be small enough so that you don't run into this problem. Of course, the second reason, which is a much, much better one, is that this excludes the most interesting examples. Code subspaces that include, for instance, typical black hole microstates. Right, these would be very large code subspaces, and well, we want to be able to talk about this type of thing and reconstruct this type of thing in AdS CFT. So what do we do? Well, we can embrace the fact that we have this state-dependent reconstruction, or we could do a thing that is often done in quantum information theory and ask, what's the worst case? What's our worst case reconstruction? Surely there has to be some region that we can always reconstruct no matter what. What is the state-independent reconstruction? How much of the bulk can we reconstruct in the state-independent way? So, question. So how much of the bulk is reconstructible without state dependence? So clearly, this is going to depend on your code subspace. But for a given choice of code subspace, it's going to be the worst case scenario. In other words, within your code subspace, you find the quantum extremal surface that's closest to the boundary. And we say, okay, that's what I can reconstruct in every state in my code subspace. And therefore, within this code subspace, this reconstruction is state independent. So find the worst case quantum extremal surface, the one closest to R, your boundary subregion. And this is the worst quantum extremal surface in your code subspace. And then you say, okay, everything inside of the entanglement wedge of this worst case state is reconstructible without state dependence. Okay, so this is what we can do. Now, at this point, I should really be putting down a new section header, which will give away the answers to what this state is.
Can I ask a question here?
Let me stay what the state is, and then
sure,
you can ask your question, which is the role of the maximally mixed state. Okay, now you can ask a question.
So why are you taking this to be closest to R? I thought with HKLL, you could just construct everything up to the causal wedge anyway.
Yes, but so this is an important question. Let me draw a picture. So suppose that I have boundary region D of R, this is CR. And in some state of the code, in the code subspace, I have a quantum extremal surface here. Let's call it X1. And then in another state, I have another one, X2. And in a third state, I have an X3. All of these will always be outside of the causal wedge. That's causal wedge inclusion. But so HKLL will get us up to here, but then we'll ask, okay, how much further can we reconstruct without state dependence? And that will be, in this case, X3 is the worst case scenario. So we'll say, okay, everything in here can be reconstructed in our code subspace without state dependence. Everything else is going to be a state dependent reconstruction. Can that answer your question?
Yeah, understood. Thank you.
Other questions? I'm going to assume that it's all crystal clear and not clear as mud. Okay, so the role of the maximally mixed state. So the relevant state, as you might have surmised at this point, is that it is the maximally mixed state that gives you the correct quantum extremal surface that demarcates the region that you can reconstruct in a state independent way versus the region that has to be the reconstruction is going to be state dependent. So it is the QES of the maximally mixed state in your code subspace.
Excuse me, I know I'm late, but can I ask a little small question?
Sure, go for it, yeah.
I'm not sure, it's probably naive, but how exactly is this notion of far away from the boundary defined in a different?
Good, yeah. So what you want to ask is, what is the outermost, by outermost, I mean, in terms of, what is the outermost quantum extremal surface? So put differently, which quantum extremal surface is contained in the entanglement wedges of all the other quantum extremal surfaces? Now, you might have been concerned and said, well, how are you guaranteed that there even is one? Maybe all of them have these sort of overlapping entanglement wedges that, you can't actually be guaranteed that there is one. But it turns out there is one. And there is going to be, there's always an outermost quantum extremal surface. You can prove this. And that's the one that we mean closest. When I say closest, that wasn't a precise statement. The precise statement is the outermost one.
Thanks.
Other questions? Okay. So it is the QES of the maximally mixed state within one that's maximally mixed in your code subspace. So it has support only in the code subspace in terms of how it's maximally mixed. That is the surface, that is the QES that determines the state independent reconstruction. And this insight was derived in this very beautiful paper by Patrick Hayden and Jeff Pennington, using the language of approximate quantum error correction, 2018. Now, I'm not going to talk about approximate quantum error correction. It would take me way too long to introduce this, but I do want to sort of give you an example of this type of thing at work. The sort of a very recent example of the way that the maximally mixed state works, and evaluating the quantum extremal surface of the maximally mixed state, how that changes your reconstructability. So this is from a very recent paper I wrote with Jeff Pennington and Arvind Shabazzi-Moghadam. So example of
sorry, I just have a quick question.
Of course.
So in the case where you choose your code subspace to be infinite dimensional, you wouldn't have a necessarily well-defined maximally mixed state, right? So is the answer to that you always choose the code subspace to be finite dimensional because those are the ones that you're interested in, or?
Well, you could answer it that way. You could say, oh, we're doing quantum gravity. Really, our code subspace should only be finite dimensional. But actually, in practice, we often do want to work with code subspaces that look like they're infinite dimensional. So in that case, we typically would say pick the thermal state, and that's good enough. Yeah.
Okay, that makes sense. Thanks.
Other questions? Okay, so example of this at work. So this is very recent work by myself, Jeff Pennington. This is from last month, and Arvind Shabazzi-Moghadam. Okay, so let's. This is a sort of an example of how typicality. It's very important for you to have this type of state dependence if you're looking at typical state black holes. So let's suppose that we're looking at a black hole that's roughly in equilibrium. We're going to model it at equilibrium. We imagine this is a black hole that formed dynamically in some way. It's a single-sided black hole, but enough time has elapsed that by now it's going to be in equilibrium. So some late time black hole formed dynamically and roughly at equilibrium at late times. So this isn't, there's no evaporation here. This is just a black hole that's sort of equilibrated at this point. So we can approximate this at late times as AdS Schwarzschild, even though at early times they have to be very different because it's formed dynamically. So, okay, at late times, look something like this. But we know, and we don't care what it looked like at early times. And we're going to be looking at some late time Cauchy slice. And we're going to say, okay, so this is approximately an equilibrium. So at late times, we're looking at the bulk fields being in the Hartle-Hawking state. Again, there may be some corrections to this, but they look like they're in the Hartle-Hawking state. That's fine. We're going to approximate them in the Hartle-Hawking state. Now, want to do any kind of bulk reconstruction, we better pick a code subspace. Let's be very ambitious. Let's pick our code subspace to contain basically all typical states of black holes that have smooth horizons. So we're going to take our code subspace to contain all microstates with a smooth horizon. So expect this is of dimension e to the a over 4g, what is the area of the event horizon at late time. Now, suppose we want to say we would like to reconstruct some operator over here. If we want to be able to do any kind of reconstruction, we have to be able to turn on operators, right? Which means that we have to expand our code subspace to not just include the Hartle-Hawking state, but to include other states of quantum fields in this background. So to do reconstruction, we need more states in our code subspace. So in particular, we're going to want to, let me blow this up. This is our event horizon. We want to do reconstruction on something over here. Then we say, all right, we want to turn on some operator here. We need to be able to have, in addition to the e to the a over 4g states that we have, we need to also be able to excite some states over here. So we add more to this. And now we say, okay, so now we have a code subspace, which contains non-trivial states of the quantum fields that are, in particular, of the right moving modes that are straddling the event horizon. And so we say, okay, we want to do bulk reconstruction, and we want to do state independent bulk reconstruction. That tells us that we're going to look for the maximally mixed state of these modes. And so reconstruction, that is state independent reconstruction, requires us to ask, where is the entanglement wedge of the entire boundary in the maximally mixed state? So I mean, redraw this picture. This is A, and we think of this wave packet as A and B. Sorry, put this back. Then we're looking for a state where A and B together are maximally entangled with a third subsystem. And as it turns out, in this state, what you find is that there exists a quantum extremal surface that is not present in the Hartle-Hawking state. So in this maximally mixed state, there exists a quantum extremal surface not present in the Hartle-Hawking state. And it sits actually right up to sub-leading order in G Newton. It sits right on the event horizon. Chi of square. Now, as it turns out, because we have such a large code subspace, we have e to the a over 4g black hole microstates. It turns out that chi-I actually is the minimal quantum extremal surface in the maximally mixed state. So chi-I is not just some non-minimal irrelevant quantum extremal surface, but it is the minimal QES in the maximally mixed state.
Netta, could you say again why you drew two sets of modes? I thought if you just wanted to make a code space of operators that lived entirely behind the horizon.
I want to be able to turn on operators anywhere I want. So
okay,
yeah, I mean this is shouldn't take this picture too seriously, you know. I mean,
okay,
it's,
sure.
Yeah. So chi-I is the minimal quantum extremal surface in the maximally mixed state. It sits on the event horizon, and that tells us that reconstruction of any operators behind the event horizon in this large, very large code subspace is always going to be state dependent. Now, we're not the first ones to notice that reconstruction of the black hole interior has a lot of state dependence in it. But what I want to emphasize here is that this is the quantum extremal surface in the maximally mixed state is a geometrization of the state dependence of the black hole interior. So it's been noted by many people in many different ways that state dependence is one possible way of saving you from the firewall problem. If everything in the black hole interior is the reconstruction of it is state dependent. And so what we find here, and again, we're considering a code subspace of microstates with smooth horizons. Keep that in mind. And what we find is that indeed there exists a geometric avatar for the state dependence of reconstruction behind the event horizon when you have these microstates with a smooth horizon. So the QES of the maximally mixed state is the geometric avatar of state dependence of the black hole interior.
I have a question.
Go for it.
So if you started with a code subspace that only contained smooth horizon microstates, why is it, I suppose, surprising in quotation marks that you can have reconstructions without firewalls?
Oh, it's not. I did not say that this was that it was surprising that we can reconstruct it, or that it's surprising that there are no firewalls. What I said is that if you take the arguments that state dependence buys you out of firewalls, and then you ask, how do I see geometrically the state dependence in the reconstruction? This tells you, aha, it's that quantum extremal surface. That's the geometrization of the state dependence that can get you out of the firewall problem. I mean, whether firewalls exist or not, or non-smooth horizons, I haven't said anything about that.
So I also have a question. So it sounds like smooth horizon does not imply local modular Hamiltonian then, because otherwise they would all have the same chi-I. But I guess the intuition wasn't the intuition that I guess if it's a smooth horizon, it looks Rindler, and then that does have a local modular Hamiltonian.
So you have to be careful whether you're talking locally or not. So certainly if you look at very late times, you say, oh, there's an event horizon, the black hole is very close to being stationary, the modular Hamiltonian, you might think, okay, well, the modular Hamiltonian is going to depend on the entanglement wedge. So even if your event horizon looks locally like it's stationary, the entanglement wedge could be way behind the event horizon. And then the modular Hamiltonian is evaluated on the boundary of the entanglement wedge. You can think of it as boosts along the boundary of the entanglement wedge, not along the event horizon itself. So the modular Hamiltonian depends on the entanglement wedge rather than on the causal wedge. So even if if your black hole looks like it's stationary at late times, that doesn't mean that you get to say that the modular Hamiltonian is local.
Thank you.
I have one more question. So this surface chi-I, if you include those subleading terms, does it move in or out?
Well, our analysis was to sub-leading order in G Newton, and you are welcome to do the analysis for sub-leading order in G Newton and see where it takes you. I don't know. I mean, I would expect that it lives just. I would expect that further corrections will slightly shift it in this direction, but I haven't done the math on that. Other questions?
May I ask a question? So maybe I have some bad intuition and you can help me change that. So if I were to just think of trying to compute the area of the black hole and think about that in terms of none of this quantum entanglement surfaces or any of that, or quantum extremal surfaces, excuse me, then I would say it's the surface that wraps the horizon, right?
Which surface?
It would be an RT surface that wrapped the horizon.
No
Is
such
that
thing.
right? So help me understand.
There's no classical extremal surface in the one-sided black hole formed dynamically. There's no classical. There's no RT surface there. You're thinking about the Schwarzschild black hole, which is not formed dynamically.
Okay, so then help me understand why that doesn't work here with something that's.
So let's imagine we have a black hole formed from collapse. If you want to take a cross section of the event horizon, that's not going to be a minimal surface. It's not going to be a classical extremal surface. There is no classical extremal surface in this spacetime. So what you're proposing to use the Ryuta-Kenagi proposal instead is just going to always give you the answer 0 for the von Neumann entropy. And it'll always tell you that you can reconstruct the entire black hole. But that doesn't take into account the subtleties that come up when you try to include quantum corrections, which then tell you that actually, no, you can't, not in a state independent way.
So can you just say that statement again? So this is for, you said this is a dynamically created black hole.
Right.
Okay.
Yeah. So for Schwarzschild, you have an extremal surface there. And so you could say, oh, let me evaluate things just using the classical extremal surface. I mean, of course, if you do that, you could run into problems like violating causal wedge inclusion, because as you add quantum back reaction, it's possible for your causal wedge to actually move outwards and to contain your extremal surface. And then and so you could run into various inconsistencies.
Okay. Thank you.
Other questions?
I have a question.
Yeah.
So I understand to calculate the RT surface is just a complicated GR calculation in general, but can you just give a flavor of how you add the quantum corrections? Like, do you actually do some serious quantum field theory calculations here, or do you use some? Oh, okay.
It's very hard. In fact, I think even though Aaron and I proposed the quantum extremal surface formula in 2014, the first example of an actual explicit calculation of a quantum extremal surface wasn't done for 5 years after. So it's hard. You have to compute the von Neumann entropy of the bulk quantum fields, and then you have to extremize that. So
this isn't something that's done in quantum field theory that you find in quantum field theory textbooks. This is something you developed?
But then you have to worry about the fact that you have this this curved background. So it's a quantum field theory on a curved background, which is interacting with your metric.
Yeah. So what I'm asking is, like, what kind of calculation is this? Like, just, I have never seen this before, like doing an actual honest to goodness calculation of entanglement entropy in quantum field theory.
Yeah, so I can tell you, so in 2019, we actually did a calculation of the quantum extremal surface. And we did it in 1+1 bulk dimensions, although you can do an analysis in higher dimensions, but it's a little bit less explicit. And basically the idea is this: you say, okay, let me imagine that I have some interval, with some endpoint that I'm not going to specify. And let me compute the entropy of an interval using various methods, like if you imagine your bulk theories of conformal field theory, you can use various CFT techniques to compute the entropy of this interval, which you've been studying all week. And then you say, okay, so I've obtained the entropy of this as a function of the endpoint, let's say. And then I'm going to say, okay, let me now write down a formula for the area of a point, which is.
Sorry, so you're assuming that you're in the CFT vacuum state or something like that?
Good. So you have to know the state. And for the particular calculation we did, we started out with the CFT in the thermal state, and then we had it evolve. So essentially the idea was, well, okay, I suspect that Ahmed will talk about it in a lot more detail, but the basic idea is that you have, you break up the state, you have some left movers, you have some right movers in your two-dimensional CFT, you compute the entropy because you know the state of each one of the sectors. So you can compute the entropy on an interval, and then you have this as a function of the point because you know what the bulk state is. In that particular problem, we prepared the bulk so we knew what the state was. And then you add that to the area, and then you extremize over the location of the endpoint of the interval. Okay,
that helps. Thanks.
Yeah, so these are two papers from 2019, one which is less explicit but more general, by Pennington in 2019, and one by Almhiri, myself, Marolf, and Maxfield, also 2019. If you want to look up the calculations. This one is very explicit. This one is a little more general.
Okay, thanks.
Other questions? Okay, in the last 15 minutes, I want to talk about reconstruction complexity. So this was a question that came up several times this week. So how hard is reconstruction? So some of you have expressed the following sentiment in at various points this past week. Something along the lines of, well, sure, we can reconstruct the entanglement wedge, but also it has to be a lot harder than reconstructing the causal wedge. So I've heard various iterations of this statement this past week. And so is this true? Is this false? Well, yes and no. There's sort of, there's some aspects of this statement that are true and some aspects that are false. But in order to begin to unpack the statement, we have to be able to understand what we mean by how hard is it to reconstruct something. And of course, what I'm talking about here is the complexity of reconstruction. So for this, it's going to be extremely useful to use a tensor network model. I'm not going to subscribe to a particular model, perfect tensors or happy code or anything. I'm just going to say, suppose we have some tensor network, a model of the bulk. It's a lot easier to see this whole complexity business there. So hopefully you all attended Michael's course. So then you've seen these tensor networks before. So now suppose we have some tensor network representation of our of AdS CFT with some combination. Our tensor network has some combination of isometries and unitaries. So let me attempt to draw a tensor network. So we have these are going to be isometries. These squares are going to be unitaries. And it's going to be more isometries here. I apologize for the drawing. Should have given myself more space and so on. So we have some tensor network here. I haven't told you what kind. I haven't subscribed to any particular model. Just some tensor network consisting of unitaries. Maybe let's give it additional links describing the bulk degrees of freedom that Michael sort of alluded to this briefly at the end of the lecture today. It's not super important for what I'm about to say. I'm just going to put it down. Okay, so this here looks like the minimal cut of the tensor network. That's the sort of Ryuta-Kiyanagi cut of the tensor network. And we say, okay, so this is a representation of our entanglement wedge. And this tensor network tells us, okay, this is what we need to reconstruct. We sort of have to push through this tensor network to get to the asymptotic boundary. And this here is the minimal cut. which is either RT or quantum extremal, depending on the regime you're working in. So what we can ask at this point is we can say, how many of these isometries and unitaries do we actually need? So what is the size of this network, of this quantum circuit? How many of these local unitaries and isometries k-local isometries and unitaries do we actually need? And that's in a sort of intuitive sense, or rough sense, what we mean when we say, when we talk about how complex the reconstruction of the entanglement wedge is. Now, I've defined this in terms of tensor networks, and complexity is hard to quantify in terms of quantum field theory. So I'm going to keep on referring to it in terms of tensor network as sort of the size of the network, the number of these unitaries and isometries that you need in order to build this this quantum circuit that builds the bulk for you, reconstructs the bulk for you. So I'm going to make two points here that are important. So one, points to note. So reconstruction of the bulk region, of a bulk region, is possible from a given boundary region whenever the tensor network, the entire circuit from this to that, is an approximate or an average isometry. This is not super important for now, but that's the important thing. We need to be able to start out with some small number of legs and grow to a large number of legs and get to the asymptotic boundary. And in particular, there needs to be no smaller cut somewhere over here. Otherwise, we could not do the reconstruction up to there, because this would then not be the Ryuta-Yanagi surface. So this needs to be the globally minimal cut on this tensor network. That's what I mean when I say, this whole thing has to be an approximate isometry. It can be, unitaries here, it's fine. Not every tensor has to be an isometry, but the whole thing overall needs to be an approximate isometry. So 2, reconstruction is harder the more unitaries and isometries are more complex you have. Now, let's ask ourselves, let's go back to this earlier question up here. So where we say, well, we can reconstruct the entanglement wedge, but it has to be harder than reconstructing the causal wedge. Anybody see the causal wedge on this tensor network, or how we would even begin to identify the causal wedge in this tensor network? It's not locally minimal cut, doesn't have any local special properties. Not clear why the causal wedge would be so important from the perspective of defining the complexity via tensor networks. But it looks like it's important, minimal cuts, maybe locally minimal cuts. These are things we can identify, but certainly not something like the causal wedge. It doesn't have an obvious avatar in here. So it's not clear going from, let me draw a picture here. So here we're looking down at the bulk. So this is our extremal surface, and this is our causal surface. So from the point of view of this tensor network, it's really not clear why going from here to here should be any harder than going from here to here, beyond the fact that, well, the deeper you go, the more of these tensors you need to tack on. But why there should be some kind of a demarcation or cutoff between the causal surface, everything outside of the causal surface and everything that's behind the causal surface, that doesn't seem like it's relevant at all. So the only regions that actually play a special role are these locally minimal cuts, which we can think of as quantum extremal surfaces, either local or globally minimal ones. So intuitively, at least from the perspective of tensor networks, the locally minimal cuts i.e. QESs, appear to be the only relevant surfaces for complexity. Potentially relevant.
Netta, you have 5 minutes.
Okay, thanks. Potentially relevant. We haven't yet said how they're relevant. But I do want to draw sort of a picture here where we have multiple quantum extremal surfaces, some of which are, one of which is minimal and one of which is not. So this is going to test my drawing skills again. Let's try it. So now I'm going to have these isometries. Another one of these isometries. And okay, so then this, and I'm going to use squares again, but this time the squares are not unitaries, okay? So just ignore the previous picture. This is not, the symbols don't mean the same thing. So first couple of triangles. All right, 1, 2, 3, 1, 2, 3. And now I'm gonna have a square here, and a square here. This. Okay, so this is an example of a tensor network, which has, 2 local minima. So 2 QESs, we have QES1 and QES2. But this one has just cuts through 2 legs, and this one cuts through 3. So this is the actual minimum. So we can actually reconstruct everything from here all the way to the asymptotic boundary. This whole thing is the entanglement wedge, even though there's another QES here. So everything, again, can be reconstructed from this all the way over here. But you may notice that these objects here, these squares, these are not unitaries, and they are not isometries, at least from the perspective of moving from this direction to that direction. These are tensors that take 2 legs and give you 1 leg. So the squares equal something called post-selection. And post-selection essentially is conditioning on a particular outcome. And you can show that if you want to simulate post-selection using unitaries, you need an exponentially many unitaries in order to do this. So post-selection is exponentially complex. If you wanted to replace each one of these post-selecting squares with a bunch of unitaries, you'd be making your tensor network incredibly complex, exponentially complex. So let me draw a space-time diagram now. So here's D of R. You can just talk about the entire asymptotic boundary for the moment. So we have some chi2 and we have chi1. So everything in here is reconstructible, but we expect the things that lie between chi1 and chi2 are exponentially complex to reconstruct. That's where we expect extremely hard reconstruction. And so imagine, so a Cauchy slice that sort of goes through both of these would have the shape very analogous to this tensor network. Sort of looks something like this. So here we have chi2, I called it. This is chi1, and this is what we call chi bulge. So we have 2 local minima, and we have, as a result between them, a local maximum. And so this observation that this looks like this tensor network with post-selection is what motivated the so-called Python's lunch proposal, which was proposed by Brown, Caribbean, Pennington, and Susskind. And this proposal says that the complexity of reconstructing operators between chi1 and chi2 is proportional to the exponential of 1/2 of the generalized entropy of chi bulge minus the generalized entropy of chi2, this non-minimal, but this non-minimal quantum extremal surface. So this is the Python's lunch conjecture, which tells you about reconstruction complexity. But for those of you who are very attached to the causal wedge, might still say, well, okay, I agree with the Python's lunch proposal. I agree that it's exponentially hard to reconstruct everything behind chi2, but it doesn't tell me that it's not also exponentially hard to reconstruct everything between chi2 and the causal surface. So this proposal is, it's sufficient. It tells you that some operators are exponentially complex, but it doesn't tell you that these operators between chi2 and the causal surface are not exponentially complex. So you might say, actually, I should be okay. I should be fine. And so for that, you need the so-called strong Python's lunch proposal. So this was again in this recent paper by me, Jeff, and Arvin, where we said that the only source of exponential complexity of reconstruction is non-minimal quantum extremal surfaces. Now, I know I'm close to being out of time, or maybe I'm out of time, but I'm just going to go a couple of minutes into the Q&A to wrap up nicely. So how well established is the strong Python's lunch proposal? Well, at the classical level, you can prove this, the physics level of rigor proof. What about the quantum case? Well, in the quantum case, it appears that it has to be false, naively at least, because you would say, okay, let me go back to this one-sided black hole. But now let me imagine that I'm working in a particular microstate, so small code subspace. And let me suppose that I want to reconstruct. I imagine, so here I am with this over here, and I'm saying, okay, I want to reconstruct some operators behind the event horizon. This is a one-sided black hole. I know it's microstate. This is a very small code subspace, and there's no quantum extremal surface in the non-trivial quantum extremal surface in this spacetime. So that means that it must be simple to reconstruct these operators. However, if you take these operators like this that are very close to the horizon at late times, and you evolve them backwards in time, then they blue shift. As they blue shift, they get trans-Planckian. And we expect that in that situation, they have some strong quantum gravity effects, and we expect that those are very hard to reconstruct. And yet there's no quantum extremal surface here. So what is a strong Python's lunch proposal false? And the answer is no. You actually have to evaluate the quantum extremal surfaces, just like in the reconstruction, in the maximally mixed state. So the addendum to this, that the only source of exponential complexity of reconstruction is non-minimal QESs in the maximally mixed state. Okay, so let me just make a couple of parting comments, and then I'll finish. So
can I ask a small question on this?
Yeah, what was that?
So a small question about this. On the you need to consider maximum mixed state and then on the minimal QS. So it means this case it would be exactly on the event horizon, just like before.
It would be exactly the same quantum extremal surface as before. The only difference is that because we have a different code subspace here, in here this quantum extremal surface is non-minimal. whereas before it was minimal because we were in a larger code subspace.
But this anyway agrees with the statement that reconstructing whatever is behind the horizon would be extremely complicated.
So in this case, if you're looking at late times of this particular microstate, it will be highly complex. But what if you're looking at early times? Then, things are different. So let me, so this mostly concludes the lecture. So let me just say a few sort of parting words here. So we've seen the evolution from, Ryu Takenagi sort of classical computation of the von Neumann entropy using this classical static bulk, all the way to quantum extremal surfaces and all of the fascinating subtleties that come up with quantum extremal surfaces that come about as a result of state dependence, where the quantum extremal surface depends heavily on the state and the bulk. So a lot of this interesting new recent developments revolve around understanding this relationship between semi-classical geometry as encoded in the behavior of quantum extremal surfaces, minimal and non-minimal, of state dependence, of complexity and relations to the information paradox. So some of my own personal take on this is that the importance of the quantum extremal surfaces for the AdS CFT dictionary to get combined with the fact that they're heavily state dependent means that there's a lot of very rich structure here that we haven't uncovered yet. And I hope that many of you will be looking into this and understanding it better in the weeks, months, and years to come. So that concludes the quantum information and AdS CFT lecture.
Thank you. Excellent. So we have a few minutes for questions for Netta.
I have a few questions, but maybe I'll start with one and give other people a chance as well.
Pace yourself, yeah.
Would you go back one page to where you drew the Python's lunch, the bulge? So I just have a question about what we might call the covariant Python's lunch. So you
mean this picture here?
Yeah. Well, I mean the space-time picture right above that. No,
yes,
what I want to know is, well, okay, on the space-like slice, it's very natural to say what you mean when you say the points between chi1 and chi2. But in the full entanglement wedge, there's a question of whether you mean the points space-like between chi1 and chi2, or all of the points in the chi1 entanglement wedge that are not in the chi2 entanglement wedge. And the latter is bigger than the former.
Absolutely, yeah.
So I'm wondering if you have any comments, or if there's any work been done on asking, whether these things that are time-like separated from chi2 are perhaps in an intermediary region of complexity.
I don't know of work that has been done, but this is something that I have been bothered by, which is we have a very definite idea of what's happening here. And then we have a very definite idea of what's happening. Well, okay, yeah, what's happening over here. So everything in this wedge here being simple. But then this region up here. So it's possible that we were talking about three different complexity classes here. So this being maybe, I don't want to call it linear. Maybe you could call it linear if you want. And this is exponential. Maybe this is polynomial. Potentially. So maybe we're looking at Q-poly. I don't know. It's an interesting question, especially because you could imagine that if you turn on some perturbation here, and you turn on some perturbation here, then sort of the classic story where, well, maybe these end up right there, and then what's going on right in this point over here.
Yeah, you would sort of think that because those points because the past light cone includes points within the Python's lunch, maybe everything there has to be exponentially complicated because it's going to include something that's exponentially complicated.
Right. So that sort of goes with the worst case, if it's as soon as it's corrupted by something that's exponentially complex, then the whole thing has to be exponentially complex. I mean, there's also the fact that you could say, oh, but well, do we really, how convinced are we that things over here will travel causally, along light cones? How relevant are the light cones? I mean, I think that there probably is a situation where you could talk and say, oh, there is local bulk physics here. But I mean, it's an excellent question. I don't have the answer to that. It's something I am thinking about, but I don't know.
Cool, thanks. Maybe we can talk more another time.
Do
Sure.
other people have questions before John asks his other ones?
I guess I have a question.
Mhm.
So in the case, it's about the JLMS formula. So in the case where some of the holographic description of the system, or whatever you want to call it, is not actually on the boundary, but is some kind of abstract, extra system.
Yeah.
That could be Hawking radiation, could be something else. How much do we know that JLMS still holds?
I don't think that there is a good formulation of, at least I don't know of a good formulation of JLMS that includes state dependence of the entanglement wedge. And the type of situation you're thinking about is extremely quantum extremal, in the sense that it's this exact situation where different states will give you different quantum extremal surfaces with dramatically different specific by this, this middle region that is missing. So I don't know of a good version of JLMS for that. It would be very useful to have one. I guess I would expect that it needs to have something like approximate quantum error correction built into it, which naive JLMS doesn't have. So I don't think there's going to be an obvious generalization, but I think once the generalization is obtained, it'll be obvious. Why didn't we see this?
Right. I guess by JLMS I meant like not only just correspondence of relative entropies, but also like if you add the area term, that might vary depending on the if the external surface jumps, then you would still have approximate equality between like the sum. I mean, the difference of the area term plus the relative entropies or something like that, right?
But the problem is, how do you compute the relative entropy, the bulk relative entropy? Because you have to decide what wedge you're evaluating the modular Hamiltonian in, or what wedge you're defining the modular Hamiltonian in, right? So you have to say, so if I have some global, so two global states in the bulk, rho and sigma, and I have two quantum extremal surfaces. So this is the quantum extremal surface in the rho state, and this is the quantum extremal surface in the sigma state. Then I have to ask myself, when I'm computing the relative entropy, I have to be asked, okay, do I compute? So I want something like this, but I have to say, okay, is my sigma, the reduced state, the reduced density matrix sigma, is it evaluated on this, or is it evaluated on the smaller wedge, that? And if you evaluate it on this larger state, then it doesn't have an obvious interpretation in the dual field theory, because that is not the entanglement wedge in the sigma state. And if you evaluate it in this state, then you're trying to compare two states that are defined on different Hilbert spaces. And once again, you run into a problem. So I think the thing that you're going to have to modify in some way is what you mean by the relative entropy of these two states that either don't live in the same Hilbert space, or just one of them just doesn't have an information theoretic interpretation in the dual theory. So I think it's not the area term so much as the relative entropy term that's going to have to change.
Right, that's very interesting. Thanks.
Can I ask a question?
Yeah.
So I was wondering, if we consider this tensor network feature on one slice, right? And we evolve that slice having, say, a unitary on the boundary to evolve to the next time slice, let's say. So in that way, basically we expect the complexity to increase. So I was wondering if we have a picture of how the growth of complexity in this tensor network would work, and if we have any relationship between that and maybe the complexity equals volume or action.
Yes, certainly. So you would expect that as you evolve unitarily, you would expect the tensor network to grow. So you'd expect more and more tensors, which of course translates into a more complex network. And that's sort of a tensor network perspective on, you could say tensor network perspective on complexity equals volume on the growth of the ER bridge. Now, so there, in some sense, you might say there are two different notions of complexity here. One is a notion of oh, if I just want to, prepare the state, what's the tensor network that I'm looking at? And the other one is, well, okay, if I just, start here and I want to reconstruct everything from this boundary, then how complex is that? So for one of these, this post-selection is very important. And for the other one, you could maybe not worry so much about post-selection. Because you basically say, oh, if I have both boundaries, I have the entire system, and I'm just asking, how do I prepare the state from that? You're sort of less worried about pushing this in this direction. You could just say, oh, okay, well, not a problem. This thing here, well, let me just, evolve it in whichever direction is more convenient for me. So you could say, you could think of the complexity equals volume proposal as, I would say, complexity up to post-selection, where you don't worry about, you say post-selection, and considering post-selection to be a simple operation. That's kind of, because I'm not worried about which side I'm moving it. And so that, in fact, that's how I would like to think of this. I know that Lenny prefers to think of this as restricted and unrestricted complexity, which is to say, oh, if you just restrict to one side, then this is the complexity. If you have both sides, then it's the unrestricted complexity. It's really two ways of saying the same thing. I just like the idea of just saying, oh, the volume is just the thing that computes complexity, where it classes post-selection as simple. It's two perspectives on the same problem.
And on a related note, do we have actually a picture of how, given a tensor network, that tensor network grows given the addition of one unitary on the preparation of the state, let's say? Like, do we have a clear idea of how the tensor network is modified?
Well, we don't even have a good, a perfect, if you'll pardon the pun, tensor network for AdS CFT. We have a network of perfect tensor, but we don't have a perfect tensor network. And so I don't know. So given that we don't have a good tensor network description that really describes the bulk emergence precisely, I certainly don't know how we would. I mean, once we had that, then we could ask, what does a bulk time evolution do? Even if we're just looking at a static bulk space-time, and we're looking at different bulk slices, different slices of that, then we could ask that. Now, there's also the fact that tensor networks are, it's a toy model, and it's a toy model that's very, it is dependent on having, working at a constant time slice, and I don't know how to incorporate dynamics in it. I tend to think of tensor networks as more something which is really valuable for intuition, but not necessarily fundamental to AdS CFT. I suspect there are many people who disagree with me on this.
I was thinking more about like boundary time evolution more than bulk time evolution.
Oh yeah, okay. Then I think I think there are models of tensor networks that can model this, but I'm going to, I guess, defer that question to Michael, who probably knows the answer much better than I do.
Very much.
So I have a question about, I guess the reason why we like von Neumann entropies is because you have a replica trick, you can compute it from the path integral. But by the definition of complexity, you need to know about the non-dominant saddles. So can we interpret this as saying that somehow the non-dominant saddles are responsible for the state dependence?
You can certainly interpret it this way. You can say the non-dominant saddles are, if you want to think of the non-dominant, these quantum extremal surfaces, you can think of them as subdominant saddles in the gravitational path integral when you do this the quantum version of Lefkowitz-Maldacena. And you could say that these are responsible for that. It's sort of an interesting question, actually. How, in what sense does this QESs that compute entropy, how are they also computing, how are they related to complexity? They're computing, in terms of the computing complexity for you, but also they are related to von Neumann entropy. And so one trick that you can do in order to take these subdominant quantum extremal surfaces that get entropy for you, that get complexity for you, and get an entropy instead, is by doing the so-called the CPT conjugation trick. So let me draw a space-time diagram so it's a little easier to see. I'll bring back the tensor network in a moment. So suppose we have some space-time diagram, and we have some non-minimal QES here and then a minimal QES over there. and I'm going to say, okay, let me forget about everything that lives behind this non-minimal quantum extremal surface. I'm just going to throw it out. And then I'm going to say, okay, I'm going to now take a Cauchy slice of what's left, sigma 2, and I'm going to CPT conjugate it around chi2. So what does that give me? It's over here. Then I get the advantage of if I were to do this on an iPad is I could just copy and paste and the picture would look identical. Okay, so I have this sigma 2 over here. I have chi2, and then I'm going to CPT conjugate sigma 2. It's going to be the CPT conjugate. And this gives me another boundary here. With the advantage that because there are no quantum extremal surfaces in this part of the spacetime, and because this part of the spacetime is the CPT conjugate, then you're guaranteed that this is the only quantum extremal surface in the spacetime. So you can prove this. You can prove that it's the only one, that, you know, the sort of, if you gluing these together and then evolving forwards in time is not going to nucleate another one for you. This is something that Aaron and I did in 2017, 2018, and then Rafael Busso followed it up in also 2018, I want to say. So then that gets you, so in this space-time here, the von Neumann entropy of this, you know, call this rho 2, the von Neumann entropy of rho 2 is equal to the generalized entropy of chi2. So these non-minimal quantum extremal surfaces actually do compute a von Neumann entropy, but it's the von Neumann entropy of a different state. And there you can ask, how is this rho 2 related to, let's call this rho 1? And you would say, well, rho 2 is really simple compared to rho 1 because I've just removed all the exponential complexity. And in fact, it turns out that if you start out with rho 2 and you allow yourself a number of simple operations, then you can push the causal wedge all the way up to chi2 just by doing simple operations, meaning you don't add any exponential bits to the circuit. You don't do anything exponentially complex. Just you do something simple like turning on local operators. And in the corresponding spacetime, your causal and entanglement wedges coincide. So you can characterize this rho 2. And so the non-minimal quantum extremal surfaces appear to play a double role of being both computing generalized entropies, but for other states than the one you're actually interested in, and also being critical for computing complexity in the original state.
Thank you. Okay, I think we have only 7 minutes left. Does anyone have anything urgent they want to say while on the recording? Or are people happy with, okay, so nobody's screaming, then let's stop the recording. Then